Okay, welcome back. This is day 3 of our conference, and it's a great pleasure for me to introduce our Commander-in-Chief, Piotr, who is going to tell us about covariant functoriality. Yes, I got it right. Covariant functoriality of graphs.
Thank you so much, Jack. It's a bit awkward for me to thank the organizers. Let me thank the participants for participating, coming and listening. I also have to warn you that this is a proofless version of my North Atlantic and to Geometry seminar talk, which I gave in January. So if you by some freak of a chance attended it, maybe 2 or 3 people did, then it's the same talk except without proofs. All right. But I hope it will still be enjoyable to those of you who did not attend it earlier. I immediately deleted the slide with a definition of graphs, right? I mean, by now we know what graphs are and what paths are, finite paths, infinite paths. So let me skip it. But since I'm going to talk about morphisms, you know, our efforts are towards defining a right type of category of graphs. And we do not discriminate among objects. We like all graphs. We don't say they must be row finite or finite or cyclic, acyclic. No, we love all graphs. But it's really important how we define morphisms between them. Okay. So there is this very standard conservative definition of a morphism. Homomorphism between graphs is completely obvious, and it's been successfully applied. This name keeps on evading me, but there's a famous paper in Invenciones by a guy from Berkeley who used precisely this category of graphs to prove some outstanding result in a theory of 3 groups, if I remember correctly. So what's this obvious concept of a homomorphism between graphs? Well, you have a set of edges and you have a set of vertices. So you have 2 set theoretical maps, F0 and F1, okay, right here. And obviously you want them to respect both the source and the range maps, okay? So that's the obvious definition of graph homomorphism, but you know, in a way it is too little, and in a way it is too much. So on one hand side, I want to expand this category. I want to allow far more general concept of the morphism, but once I allow it and I have this huge piece of marble, I can carve in the shape I really want to see inside. Okay, so the generalizations we are interested in for the covariant induction is what I call a path homomorphism of graphs. So it is defined as a map from the space of finite paths in one graph E to the space of finite paths in the other graph F. And it has the following properties. Edges are mapped to, vertices are mapped to vertices. So f of E0 must be contained in F0. Again, just as before, we did it for edges, we must do it also for paths that the endpoints and the start points are respected by the map. And here I have a third condition, which looks very much like functoriality. So if indeed your path can be split into the concatenation of 2 paths, P and Q, then f of PQ must be equal to f of P composed with f of Q, okay? So of course, this makes sense only when the end of P is equal to the beginning of Q, otherwise FPQ is not the path. And let me observe that, in fact, if you would insist that a path homomorphism of graphs preserves the length of a path, then this would be the previous definition, okay? Because then edges would have to be mapped into edges, and this condition would basically boil down this more general definition to the standard one. But that,
sorry, Piotr, yeah. You said kind of functor.
Yeah, okay. You can make it precise. It is a fun. Yeah, you're right. Yes, sorry. Yes, I was a bit cautious, but yeah, you can make it a functor if you think about graphs as small category. If you have a small category in which you view objects as vertices as objects and finite paths as morphisms, then basically this f is a functor. Okay. All right. So obvious things out of the way. Now I would like to go back to basics. I want to see what is the most general applicable definition of a morphism for our purposes. So I want to go back to the construction of graph sister algebras. I want to really start from the beginning, and I want to do it in a slightly different way than is typically done. I mean, everybody has his or her favorite way of constructing graph-system algebras. We heard a talk about defining graph-system algebras from a groupoid, period. We had it given in a standard way by Genesis and Relations, by Francesca, and I want to do it yet another way. I want to do it for path algebras, Leavitt path algebras. And before we go to star algebras, K can be any field, all right? So now we consider following vector space. We take any graph, we take the space of finite paths on this graph, and we take all finitely supported maps from this space of finite paths to our coefficient field K. And addition and scalar multiplication are pointwise, the obvious boring ones, as Paul Baum would put it. But now it's completely clear that if you take these delta functions, they give you a basis of this vector space Ke, right? So P is a path and Q is a path. So chi P of Q is 1 when P is equal to Q and 0 otherwise. There's obviously a linear basis of this vector space. So now what we have to do, we have to define a multiplication, which means that we have to define a bilinear map from Ke across Ke to Ke. And it suffices that we define this map on basis elements, and then you just have to prove that this formula is associated, which is a boring and obvious calculation, but it is. And this is by concatenation, right? The definition of the multiplication is given by concatenation. So if I have one path like this, and I have another path with its beginning not matching the end, then they multiply to 0. So this time, this is 0. But if it happens that one path ends when another path begins, well, then you multiply it to the composition. Okay, so that's the definition, and you check that it works, and you call this the path algebra of E. All right. Now, you have a question, Francesca? Okay, now the next step, which is important, it's kind of obvious, I know, but I want to emphasize it. Let's not take it for granted. You construct extended graphs. So the idea is that you keep the same set of vertices. Vertices are unchanged, but you double the space of edges. I'm sorry, if you want to have some question, just ask me because it's disturbing for me. But now when it comes to edges, you say you double the space of edges. So for every edge that you have in your graph, you add another edge which goes exactly in the opposite direction. So formally speaking, you say, all right, so if I look at the beginning of the edge E star, so this is E, this is E star, then the beginning of E star is the end of E, and the end of E star is the beginning of E, okay? So this gives you an extended graph. And now that you know what is an extended graph, you can guess even by the very notation that I needed to define the star structure. I can define the Kohn path algebra. So for any graph E and any field K, the Kohn path algebra of E is the path algebra of the extended graph. So this is important, that this is the path algebra not of E, but of the extended graph. But then it's divided by the ideal generated by the Kunz-Krieger relations of the first type. Okay? Which means basically that if you multiply the edge E star with F, if E is different from F, then you simply get 0. But if F is equal to E, then you just get the projection associated to the endpoint of the edge E. Okay?
Piotr, actually, in this way, you get from the category a groupoid. So the extended graph now has the inverses, right?
No. This is. I'm not saying that if you look at this loop, I'm merely saying that. Whoops! I have to switch it to the marker. I'm basically saying without fancy notation that E star E is the end of E.
Projection.
But I'm not telling you yet anything about this. And the Kohn path algebra is nothing. Yeah. But if you remember yesterday's example, I think it was Elmar. Yeah. he talked about the Teplitz algebra. So look, what is the cone path algebra of just a simple one loop graph? Okay, so if one element, if you look at this relation, all that you have is that E star E is equal to 1. You have only one projection, and this is 1 in your algebra. Okay. So when you take the universal, you can take the algebra with such a relation. Well, this will be like pre-Teplitz algebra. I mean, you give it the obvious star structure, you pick up the field of coefficients of the complex numbers, you close it, and then you get the Teplitz algebra. Okay. And I'm going to show you that this is in fact the Levitt path algebra of a different graph, the usual Teplitz graph. But then first I have to define for you Levitt path algebras. So basically, in order to get Levitt path algebras, we take cone path algebras and we divide them by the second Kunst-Krieger relation. Okay? I mean, you can do it in one go. You can say that I can take the path algebra of the extended graph, and then I divide by two relations. So I can say that I take the cone path algebra, and then I divide it by second relation. It comes down to the same thing. And here, well, it was already mentioned many, many times, but I have to recall it, that the second Kunst-Krieger relation is valid only for regular vertices. So vertices that are neither sinks nor infinite emitters. Otherwise, the sum is problematic. And now, if you look at this definition, or you know what Levitt path algebra is, and I think that today's last talk will be about Levitt path algebras, the Buenos Aires talk. Well, then you can see that if you take the cone path algebra of, oops, I have to change the marker. Take the cone path algebra of this one loop graph, okay? And you verify that this is the same as the Levitt path algebra, but of the Teplitz graph, okay? And as I was telling during Elmar's talk, this is actually a universal phenomenon. It's a completely general theorem, which says that for every graph E, there exists a graph E prime such that the cone path algebra of E is equal to the Levitt path algebra of E cone. Okay. This is a general phenomenon. It's a beautiful theorem. It's in this book, Levitt path algebras by Ferrara, right? Abrams, if I remember correctly. This is a Springer book. I really like it. And I'm not sure I remember exactly the procedure, but it's something of the sort that you take any regular vertex and you double it. I have a regular vertex, but then I have to double it. So I have another vertex over there. And then I take any edge which arrives at this regular vertex. And from the same source, I also have to put an edge to this copy of this vertex. So if you apply this procedure to the circle graph, you'll get exactly the Teplitz graph. Yeah, but it works in full generality. And now, of course, if you take complex numbers and complete it, then you will simply have Teplitz algebra. So, but of course, if you would take the Levitt path algebra of the circle graph, then it would be Laurent polynomials. And O of S1. Okay. And you can entertain yourself with some, properties, functorialities of this construction of transforming a graph from left to right, from circle to Teplitz. Yeah, that's some fun. But we don't need it. This was just a remark caused by Elmar. Well, and now let's be honest. Let's take our field of coefficients to be complex numbers. And you can very easily endow all these creatures, so path algebras, cone path algebras, and Levitt path algebras. But of course, when I say path algebras, I mean path algebras of extended graphs, okay? So you do this extended graph in order to be able to define the star structure. Obviously, your vertices are self-adjoint. And you say that chi E star is just chi of E star, and the star of chi E star is chi E, okay? And you can check that this renders all these algebras star algebras. And now this is my approach to graph C-star algebras. I mean, not mine, I didn't pioneer it, I just copied it. But this is the approach that I like the most. Then for me, the graph sister algebra of a graph E is the universal sister algebra of this Levitt path algebra. Okay, and there are some subtleties here. If you paid attention exactly to what Francesca was saying, then you might have noticed the following condition. I told you I'm not assuming anything like rho finite. I have infinite emitters and all these nice things. Well, how about the condition when you have an infinite emitter? So say E is an infinite emitter. V is an infinite emitter, which means what? That I take, hard to write with an eraser. I take the preimage under the source map of my vertex V, and I count the number of elements, it's infinite, okay? So I have an infinite emitter. I look at the projection, which is associated to this infinite emitter, and I cannot write this infinite sum. Well, but what I can write the following demand. I can demand that chi E star, which is very easily verified to be a projection, is a subprojection of chi V. And this has to hold for any E inside the preimage under the source map of a vertex. Okay, so this was the condition which Francesca wrote, and that's in what I would call the original definition of graph sister algebras, and you should note that it's lacking here. Well, but it's not an omission, it's not a mistake. It's been ages ago, we sorted this out with Mariusz, and you can prove it at complete level of generality. It works for any graphs. When in fact this condition is tantamount to the path algebraic condition, namely that when I take the projection associated with the beginning of an edge, and I multiply it by this partial isometry associated with the edge, well, then this is just this partial isometry. Okay. So in our case, when we define our algebras as quotients of path algebras, that's part of the definition of path algebras by concatenation. If I concatenate, I mean, a vertex is also a path of length 0. If I have a vertex, which is the starting point of an edge, and I multiply it by an edge, I just get this edge. Okay. So this condition is already part of my relations. And now you can prove that indeed these two conditions are equivalent. And I have at least two witnesses, Jacopo and Young, who attended my lecture course at CISA when we proved all of this in detail. Okay. So it's completely equivalent to the old definition. I prefer it because it's, in my opinion, more neat. This condition doesn't look algebraic. I mean, at the end of the day, it is algebraic. Anyway, what is most important is that it's completely equivalent. Okay. So now that we have defined graph sister algebras, I can start my talk. This venue of research was inspired by the following diagram. And maybe let me begin by explaining the geometrical topological meaning of this diagram. And then I will explain it to you in terms of sister algebras. So in the classical setting, if you just take a unit disk, you take its boundary circle, okay? And then you shrink this boundary circle to a point, what will you obtain as a push-out? Well, of course, you obtain the two sphere. Okay. And basically, this is a quantum version of this classical picture. So maybe I should also write some arrow here. Okay. It's also injective. And this is surjective. So you have in this push out, you have one injection, one surjection. And this is very natural in topology. When you study push outs, you want to go beyond simply taking the set theoretical unions of spaces. When you have two injections, basically all that you push out is the union of sets. And it's very important to be able to do something more, at least on one leg, because in order to preserve a Mayer-Vittorius principle, like to compute a theory from a 6-term exact sequence, all that you need is that one of your maps on sister algebras is surjective. Only one is sufficient. So this means that the level of compact Hausdorff spaces for me is completely sufficient that at least one of my maps is injective. Okay? The rest is very important to allow this freedom of not being injective to, for instance, explain such important examples. Okay, so this is how it looks in terms of the topology. And now let me explain it to you in terms of sister algebras.
Sorry, I have a question
Sure.
about the directions of this.
Haha, that's a very good question. Yes, I will come to it. Yeah, this is a very good question. That's part of the point. It's not a mistake. Okay, so here, when you look at this graph, we already discussed it at length, that Teplitz graph. So I take C star, the graph sister algebra of all these graphs. So here's the circle sister algebra. Here's the Teplitz sister algebra. This is just the symbol map, which Elmar was explaining yesterday. Well, this is just complex numbers. So this is just unit by unit map. Okay, but now that's the evaluation map.
Sorry, so do you reverse arrows now
Yes,
or not?
yes, I do and I don't.
Okay.
Just let me say it. It's coming. That's part of a mystery here. So when you look at so when you look at spaces, it's a nice, decent, honest push out. You have a push out. You take this contravariant functor of Gelfand Naimark. You get commutative sister algebras, and then all arrows are reversed, and your push out is turned into pullback. And then these two sister algebras are the same because they're commutative. Here you have continuous functions on the unit disk. So in our case, this is continuous functions on the quantum disk. This is a minimal unitization of compact operators, but we like to view it as continuous functions on the standard Polish quantum sphere. Okay. And now we also have this pullback diagram. Look up Podlesh's thesis. It's been with us forever, like 30 years or more. And you know that you have a pullback diagram with the Podlesh quantum sphere here. You have evaluation. You have one character on the Podlesh sphere. You take this evaluation. You go to complex numbers. Then you have a symbol map for Teplitz algebra. You have a unit map. You look at this diagram. Yes, this is a pullback diagram, obviously, and you have it. So now we wanted to understand this pullback diagram of sister algebras in terms of graphs, just as in the classical case. We understand the pullback diagram of commutative sister algebras in terms of spaces. And this is what really is behind this pullback diagram of commutative case is simply a certain topological operation of spaces. It's shrinking the boundary circle of a disk to a point to obtain the sphere. And here, well, at least intuitively, the same happens. I have a classical circle boundary of my Teplitz algebra. I shrink it to a point and I get the Podlesh quantum sphere. Okay, so when it comes to these two edges, maybe I'll color them. So when it comes to the blue edges, you can very easily verify that a point is an admissible subgraph in this graph, and that the circle is an admissible subgraph in this graph. So there's a standard procedure which allows you the contravariant induction. So this automatically gives you a star homomorphism going in the opposite direction. So now let me.
Sorry, what do you mean by admissible?
This definition has, Mariusz will explain it in his talk.
Okay.
Yeah, I mean, that's the easiest way to answer. I mean, Francesco was actually explaining it yesterday to some extent. The basic idea is that you take a subgraph in a graph, but it's not enough that it's a subgraph. The subgraph of a graph must be obtained in the following way, that you choose some vertices in this bigger graph, in the ambient graph that you want to kill. And the set of all these vertices you want to kill has to be hereditary, saturated, whatnot. Okay, there's a number of conditions. And then the subgraph must be obtained in such a way that you kill these all these vertices which are in this hereditary, saturated, whatnot subset. And you also kill all edges that end at these vertices, but nothing more. Okay.
So it's admissible if it corresponds to a quotient sister algebra.
Yeah, I'm not sure that there is an equivalence, but very close. So yes, exactly. But this is in textbooks. I mean, this is a ABC of path algebras. Sorry, Leavitt path algebras and graph sister algebras. Now let me reverse these arrows because it's wrong as it stands. I mean, these arrows were for graphs, but now I have these graph sister algebras. So let me write it in the opposite direction. Okay. So they are contravariantly induced, and Mariusz will speak at length about this contravariant induction and how we can go beyond of what's in textbooks. Okay. All right. But now, we also have some natural maps here. I mean, there is the unit map. We cannot deny its existence, but it's a little bit hard to interpret it in terms of graphs, except that we can easily do it using the covariant induction. So when it comes to the other two edges, let me mark them in red. Right, now I don't have to. Oops. I don't have to reverse this arrow because this is covariant induction, which is what I'm going to talk about. I'm having the same problem you had, Francesca. Okay. So we have these maps at the level of sister algebra, and somehow we want to understand them in terms of graphs. So with this one, there's not much to understand. That's the unit map. There's nothing more I can do. And well, when you look at even the most trivial definition of a covariant induction, how from a map morphism, a standard morphism between graphs, you can have a covariantly induced homomorphism between graph sister algebras. Well, there's no problem. You can map this projection to this projection, and you map 1 to 1, and that's it. But it's much harder to understand in terms of graphs the map from the minimalization of compact operators to the Teplitz algebra. We have this map. We have this pullback diagram. We have the short exact sequence. It's been there forever. But how to interpret it in terms of graphs? And then we realized that in order to interpret it as some kind of functorial induction from the category of graphs, we must allow morphisms that map edges not to edges, but to paths. And here the recipe is the following. If you look at the space of paths in the Teplitz graph, well, you have countably infinitely many paths going from vertex V to vertex W. Well, you can just go from V to W by this edge E. You can go around the loop, go by the edge E, go 1 million times by the loop, go to the edge E. So you have countably infinitely many paths from V to W. Well, and if you look at these vertices V to W, you also have countably infinitely many paths. They happen to be edges, but so what? They are just, this is a set of natural numbers by which you enumerate countably infinitely many paths on the right-hand side. And indeed, if you look at the covariant induction, which I'll explain in a second, for such a path morphism of graphs, then yes, the induced map on the level of graph sister algebras exists and gives you the desired map, rendering this a pullback diagram. Okay. So this was a motivating example, a very, very simple one. And then with Mariusz and Alex Kirvasitu, we ventured to prove something more general. Now I suppose we can have even a more general theorem, but that's work in progress. In the paper from, I don't know, 2 years ago or something, yeah, we came up with the following generalization of what we had earlier. So when you look at these two parts of our pullback diagram, well, we have that F1 is an admissible subgraph of E1, but F2 is an admissible subgraph of E2, and you have this natural textbook contravariant induction. This is the subjections of sister algebras, well understood from textbooks. Okay, but now we and indeed it came from examples like before. it's interesting to see what happens, how to complete it to a pullback diagram. But now we've these maps between C star of E1 and C star of E2 being induced covariantly. And here are some technical conditions. I suppose Mariusz will perhaps explain it in his talk, because that's he will talk more about the pullback theorems. I just want to signal for you the motivation of why we bother with covariant induction. It's not for the sake of being tidy and we have contravariant and see how covariant works. No, simply when we wanted to expand the scope of pullback theorems for graph sister algebras, we realized that the contravariant induction is just not enough. I mean, we managed to push these conditions to some higher level of generality, and Mariusz will explain it, but it's still severely restricted. And we realized that in order to get the pullback diagrams of graph sister algebras, we don't actually come from the category of graphs, because half of our morphisms are induced covariantly and the other half is induced contravariantly. And this is a bit of a puzzle, because I cannot give you a general theorem I would love to have and say, okay, this is a category of graphs, this is your, say, contravariant functor, and it turns push-offs to pullbacks. That would be ideal, but that's not the case. And this is kind of hybrid form. And maybe one day we will understand how to transform these morphisms which go in one way into morphisms that go into the other way. And then we'll say, aha, so this induction is contravariant after all. But we're not there yet. We just we play with examples and try to see what we can do. Okay, but let me get back to this particular theorem over here. Well, we have a bunch of conditions. For instance, we assume that E1 has no loops, E2 has no length 1 loops, and so on and so forth. But basically what happens here is that in your loopless diagram, you attach you attach some loops, right? Like it was with the Teplitz algebra. And there are some conditions on this F. Well, it is a functor in the sense I explained earlier when I treat E1 and E2 as categories. And the only sort of essential particular condition I would like you to bear in mind, because it changes what's happening, is that we must map paths from finite paths from E1 into what I call pointed paths. And pointed paths are paths whose last edge is not a loop. Okay. So when we looked at the Teplitz algebra case, the previous case, then it was no problem, because if you look at all paths from V to W, well, W is the same, so there is no loop. Okay, but then if you look at SQ2, there will be a loop, and the situation will change. Okay, so we have such a theorem under these conditions, generalizing this situation. But of course, we have many more examples. And what I like is that these are natural examples from the point of view of algebraic topology. But before I go into the algebraic topology, you know, it's a little bit scary to think that 85% of all graph sister algebras you bump to are Kunz algebras. So you better have a Kunz algebra on the menu. And that's exactly what we did. You take the O2. Let me just change fonts. Have a Kunz algebra O2. You have one single extension. So I know some fancy graph sister algebra here. And you have the same story. You always have a unit map. And when you take this one single extension of the O2 graph, and then you take its graph sister algebra, and then you shrink the Kunz part to a point, what you get is again the Podlesh quantum scheme. That has no classical counterpart, because O2 is a purely quantum sister algebra. And I don't think it's limited to O2. I think I could take any OM. And at this moment, you can ask, well, so fine, how about this map? How do I go from this minimalization of compact operators to this one single extension of a Kunz algebra? Well, I already told you that it's basically what you have to do. You enumerate countably infinitely many paths from V to W by the set of natural numbers given by these edges over here, okay? And you again have no problem with pointed paths because all paths from V to W are pointed. And so here it comes to play another condition, which I skipped, I'm afraid. So let me go back. You must be surjective. You must reach all pointed paths in the other set. Okay. So I look at the graph E2 and I look at all pointed paths in E2, and they must be in the image. Okay. So that's the condition. The rest is up to you. You can have many different morphisms between graphs, path homomorphism of graphs, which induce one and the same star homomorphism between C star R. Okay. So the only thing that you really have to take care about, because here all these paths from V to W are pointed, the only thing is that really all ways of going from V to W are taken care of, all of them. So of course you can have lots and lots of possible permutations. You can go 5 times around one loop and then 10 times around the other loop, or the other way around. It's all non-commutative, you know. So it's like in a free group, you have different words. The only thing is that the last word is this edge E, which goes from V to W. But still, it's countably infinitely many things. So you can label it by edges in this Podlesh graph. And yes, it's a pullback diagram, and you can get this funny presentation of a Podlesh sphere. But of course, this wasn't a motivation. It was just to see how it's applied. And I like the fact that we can do some surgery on the purely quantum space. Now, another example. Now that's purely topological. So this is the graph sister algebra of the equatorial Podlesh quantum sphere. But let me just draw a classical picture. I have a sphere, and I have the equator. And here I just have a circle, and I embed it in my S2 as the equator. But then I shrink this equator circle to a point. So what you get over here is what I like calling kissing spheres, but the professional name is weighted complex projective line. Okay, so when you shrink this equator to a point, you'll get 2 spheres that are attached by the pole. All right. And that's exactly the picture we have in the non-commutative setting. This will be, as I told you, if we have like C star of this graph, you'll have the equatorial or the generic Podlesh quantum sphere. So S to Q, let me write infinity. Okay, that's this sister algebra. And now when you collapse the space of classical points inside, well, you'll get like 2 standard Podlesh quantum spheres attached at the poles. But we have also the theory of weighted complex projective spaces. They are graph sister algebras. So that's the picture. But I don't want you to think that all I can do is to collapse to a point. Well, we can be a bit more sophisticated. You should remember from Francesca's talk yesterday that we can embed quantum CPN -1 in quantum CPN. So just to fix attention, I take n equal 2, but it works in anything. I take CP1Q, the Waxman-Soberman quantum complex projective space, and I embed it in CP2, quantum, of course. So this means that when I take the graph sister algebras of these graphs, I have a subjective homomorphism here. And again, everything works here. When you look at this graph given by 2 vertices and countably infinitely many edges between them, well, you can embed it at the beginning of this graph, and this is an admissible subgraph. Okay, you check all the conditions from textbook, and there's an admissible subgraph. So you have this canonical surjection going in the opposite direction, which basically tells you that you kill this vertex and you kill all edges ending in this vertex. And this is well defined by the properties of this vertex being a hereditary, saturated, and whatnot subset. Okay, well, here, what you have, it also appeared many times already. This is the SUQ2 sister algebra. Or if you want, you can think, and this is all we already know, this is the Podlesh quantum sphere, the standard one. So what you have here is exactly like the quantum Hopf vibration, because if you look at graphs, it's like S to Q inside S3Q, the Hopf vibration. And at the level of sister algebras, of course, you really have, yeah. And here you do not invert, because as always, I mean, as before, I mean, this paradigm that the left upper and right lower maps induce star homomorphism contravariantly, and the other two induce it covariantly.
But the map between spaces is in the opposite direction, is from S3 to S2.
What?
Is from S3 to S2, the of vibration.
test.
Of vibration is the opposite direction, the arrow.
Yeah, but yeah, but S2 in S3, this is the vibration. I mean, oh, sorry, I'm sorry, of course, yes, you're right, of course, yes, oh, sorry, yes. Mm-hmm. Of course. Yeah. At the level of spaces, you would just have, you know, S3 covering S2Q with a circle fiber, but when you look at sister algebras, then you would have the embedding. Yeah, the Podlesh quantum sphere is a sister subalgebra of the quantum SU2 sister algebra. So this is not very legible. Yeah, and so now we would like to understand this standard quantum Hopf vibration embedding the sister Podlesh sister subalgebra in the Voronozh sister algebra in terms of graphs. And the same recipe works as before if you remember that the image for my path homomorphism of graphs should be all pointed paths in the other graph. So when I look at the SUQ2 graph, and when I look at all finite paths from V to W that are pointed, then this last circle has to be ignored because it's an edge loop. I mean, I can, well, not quite, because, no, yes, of course, yes. Because once I employ this second loop, I cannot go back. I cannot follow it by any edge which is not the loop, all right? So it means that when it comes to enumerating all finite pointed paths in this SUQ2 graph, it's the same story as for the Teplitz graph. So you can just have the same map. And now it will induce a star homomorphism between different sister algebras. And better still, you'll have a pullback diagram. And yeah, I forgot to write that this is this, but it was in Francesco's talk. This is this, actually Francesco's as well. This is this Waxman-Soibelman S5. So graph sister algebra of this one by a non-trivial theorem Honk-Szymański, that's C of S5. And this,
before the ball.
Oh, that's you're right. You're right. This is the ball. Sorry. Of course, you're right. Thank you. That's the ball before. Yes. No, I there is also an equivalent picture where you have S5. Sorry about this. Yeah, thank you. That's the Honk-Szymański quantum 4 ball. Yeah. And then the Waxman-Soibelman quantum 3 sphere is the boundary of the Honk-Szymański 4 ball. Okay. And this is part of the CW complex structure Francesco and Tomek were talking about. Yeah, what we do, we take CP1 and we attach a higher dimensional cell, which is this 4-dimensional cell over its boundary sphere to CP1Q. As a result, we get CP2Q. Okay? So that's from the point of view of CW complex structure. So you see, that's this is an important pullback. And in order to understand this pullback in terms of graphs, well, for the time being, I don't have a better recipe than to have 2 arrows induced contravariantly and 2 arrows induced covariantly. But I agree, this is not a push-out to pullback diagram. That's what we are trying to comprehend. One of the hopes that we have is that when you look this path homomorphism of graphs, at least in the context of pullback theorems, then you must always assume that they are injective. So if something is injective, it's of course invertible on its image. but I'm having problems defining the domain of a map going the other way around. Maybe it should be just all pointed paths. But it's not clear to me how to do it. I take a graph, and then I want to take only the space of all pointed paths. Maybe that's the way to do it. And then you would have this, actually this morphism going in the other way, and it would be covariant induction. But we have to smooth out the details, and let me not do it in an ad hoc way. Okay, so now the technical part of my talk, I really want to explain, the soya of this theorem. When it comes to, so I have three conditions. I call them covariant conditions, and each of them is designed to allow covariant induction for respectively path algebras, cone path algebras, and finally Leavitt path algebras. And when you are done with Leavitt path algebras, it also works for graph hysteroalgebras, because the latter are defined by the universality. Okay, so when it comes just to inducing a homomorphism between path algebras, the only thing that you care about is that you are injective when restricted to vertices. And this is clear because when you look at projections assigned to vertices, then you have that chi v, chi w is equal to chi v chronicles delta vw. So these are mutual orthogonal projections. So if you would have a map that would identify them, so f of chi v is equal to f of chi w, well, when you have a projection which is mutually orthogonal to itself, which is of course impossible because projections are elements of the basis of the path algebra. So it must be injective on vertices. That's a must. Now it's getting far more interesting when you look at the first configuration. So in order to define this cone path algebra, you have a certain condition of being monotonous. And when we are writing a paper with Mariusz and Alex Kirvasitu, we assumed a stronger condition, if you remember, Mariusz. We assumed that this implication holds not just for edges, but for paths. And I think we wrote something like this: if you have f of alpha precedes f of beta, well, then we want that alpha precedes beta, something like this, okay? But this condition turned out to be too strong. I mean, there are nice natural examples where this condition is satisfied, yet you have the induced covariant functor. Maybe I should first explain what I mean by this partial order relation. Well, it's very simple. I say that gamma is less or equal than gamma prime, if and only if there exists some alpha such that gamma prime is equal to gamma followed by alpha. So if I can extend my path to the right, it's very important. I extend it to the right, not to the left. Okay. Then this longer path is bigger than the shorter path. Okay, let me erase it perhaps. So this is a very natural definition for an order. But here we assume it only for edges. And why? Because it's a very important example that, say, I have a graph which is a one loop graph of a circle algebra, and I just map everything to a point. So this is just evaluation map. I have a circle algebra. I take the evaluation map, and I get a number. This is a perfectly well-defined star homomorphism. Okay, and it's induced by mapping both this edge to a point and this vertex to a point. And when you look at this condition, well, then it's not satisfied. This condition is not satisfied if you write it for paths. When you write it like I did it, yes, it is satisfied. And of course, when you are back to edges, one edge precedes another if and only if it is equal to it. Okay, so this is why I could just replace it by equality. But here already some fun began, because it's already non-obvious that this forms a category. So you have to prove that indeed the composition of morphism with this property is again a morphism with this property. It's a simple proof, but still is a proof. Okay, but now we want to go to Leavitt path algebras. And here's a condition which is really, really difficult to explain. So let me tell you that you should look at it as a lawyer. I mean, this part is written for lawyers. Everything is precisely stated and explained and named. but it's hard to understand. So instead of explaining all these legal data, let me try to give you the gist of what's going on by drawing a picture. Okay, so when you add a regular vertex, you have a second Kunst-Krieger relation, and this is a troublemaker. That's something that really requires some effort. So if you look into the textbook of this covariant induction, then you just so edges go to edges. Okay, there's no extension that we are making, no generalization that we are making. Then the condition they have in textbooks is very simple. Take a regular vertex, so you have graph E and the graph F. You have a regular vertex here. Have a graph homomorphism, so this is V. This is F of V. So if it's a regular vertex emitting the n edges from E1 to En, well, then if you want to have an induction, covariant induction, then you must assume the regularity condition, which says, all right, that if V emits n edges, then F of V also emits n edges, and they are the images under F. So F of V1, ... F of En. And it's obvious why we want it, because then we ensure that the second Kunst-Krieger relation is well defined, and that this morphism of graphs indeed induced a homomorphism of graphs hysteroalgebras. But in the world where we don't want to map edges to edges, and to be more general, we ask ourselves the question, how can I make it more general? And the answer is the following. I start with a regular vertex, so this doesn't change. I still have, say, n edges emitted from V. But let me erase the right-hand side. Oh, I exaggerate. Okay, let me put it a bit lower. So that's my F of V. It's again a regular vertex. And now I take, say, k edges. I take k less or equal to n, bigger than 0. I take k edges emitted from F of V. So from F1 to Fk. And now I can do the following. I can look at the endpoints at these edges. Well, so first I can decide that some of these edges I leave alone, I let them be. For some other edges, I say, okay, I'm not happy with just edges, I want to have longer paths. So I look at the endpoints of the chosen edges, and I take all edges which are emitted from these endpoints. But it's very important when I have to take all edges emitted from these endpoints. Okay, I cannot just take some of them, I can have to take all of them. So this gives me some paths starting from FV, now some of length 1, some of length 2. And I can iterate the procedure. I can again, at each of this endpoint of this, I can look at all these paths of length 2. I can let some of them be. And for the other ones, I can say, no, I want to go even further. I want to extend it to paths of length 3 and so on and so forth. But again, this principle is that if I decide to extend, I have to be democratic. I have to allow everybody which comes out of a chosen path to be allowed. Okay. And I go as much as I want, but at the end of the day, the number of all thus constructed finite paths must be equal to n. And then, as you can imagine, I'm mapping these edges to these finite paths. And you can check that this regularity condition allows covariant induction. And by no means we are mapping edges to edge. Okay, so this is as general as we managed to get. And if you want to make this definition precise, well, I'm sorry, then you have to play around with this legal data. It's far more difficult to write it down, what you mean, than to discover. Okay, now I have the last 5 minutes. So this is for formulating the formulation of the main results that we have here. So as I already told you, well, I didn't mention what is this covariant induction, but it's really very obvious. I have a set theoretical map from finite paths in E to finite paths in F. And now you can see that this covariant induction is very simple. I take my basis element in the path algebra chi p. and I map it to the basis element in the path algebra of F, which is now chi F of P. I mean, F of P is again a path, this is again a basis element. This gives you a well-defined linear map. So it's obviously a map between vector spaces, but you can check that if just this one condition of injectivity is satisfied, that's it. This is a homomorphism of path algebras. Now it's a bit more tricky with conpath algebra. There is this obvious extension, you know, I wrote it here at the end. There's an obvious extension when I have a map, path homomorphism of graphs from E to F. I also have the obvious extension to the path homomorphism of the extended graph. I simply map starred edges to, so if I have, maybe I'll write it down, it's easier than talking. If I want to say what is F bar of E star, then obviously it's defined as F of E star, okay? So then indeed you have a star homomorphism once you look at the star structure. Okay, so that's what I mean by this F bar here, because P might be composed from edges coming from the starred and non-starred part of the extended graph, that we know what to do with it. And then because we also assume this monotonicity condition, you know, this one, that's sufficient actually for us to prove that this first configuration is satisfied. So lo and behold, we have a homomorphism between conpath algebras. And finally, this is where we wanted to arrive. When you also assume this difficult to formulate, but actually very easy conceptually principle of regularity, and you have all these three covariant conditions satisfied, then yes, such a path homomorphism of graphs induces a homomorphism between Leavitt path algebras. And now when you go to complex numbers, you endow the Leavitt path algebra with obvious star structure, take the C-star completion, yes, you'll have a star homomorphism between C-star. And now that's the last slide, which is the main result here. When you look at the directed graphs together with path homomorphisms of graphs satisfying the three just explained covariant conditions. So first, it forms the subcategory in the category of graphs and path homomorphisms. It's not difficult, but it requires a proof. We call this category R MIPG. R is for regularity, M is for monotonicity, I is for injectivity, P is for paths, okay? And G is for graphs. I know it looks monstrous, but I have no better idea of how to call it. And our construction in terms of objects is always the same. I take a graph E and I construct its algebra. Here I already go immediately to graph C-star algebras. And then I take this path homomorphism of graphs satisfying the three conditions. And by the recipe given here in red, I prove that this is a well-defined star homomorphism and that all of them form a covariant functor into the category of C-star algebras and star homomorphisms. But of course, you should ask a question of what happens in the unital case. Well, remember that everything, path algebras, conpath algebras, Leavitt path algebras, they are unital if and only if the set of all vertices is fine, okay? So basically what you have to do, I just change one letter. Instead of injectivity, I demand bijectivity. So when my both graphs E and F have finitely many vertices, I demand that this morphism between them is a bijection. And it's obvious why we have to do it, because the unit in all these algebras is just the sum over all vertices of these projections associated to vertices. This is the one. Okay. So when you go to the other graph, so here you'll have chi of F E, right? So one in your Leavitt path algebra, or conpath algebra will always be given by such a sum. So if you want to map one to one, and you map this element here to this element, which is the sum again over all all vertices in your graph E. Now we have these projections, but under the action of F. So you want to ensure that this is one again. The only way to do it is that you assume that you are bijective on a set of vertices, okay? And then you have this refinement of the theorem that yes, if we restrict our objects to graphs which have finitely many vertices and replace the injectivity condition by bijectivity condition, that in fact what we have here is a unital homomorphism between sister algebras. And this is exactly 10 o'clock, so let me stop here. Thank you.
Okay, thanks, Piotr. Are there any questions?
So Piotr, can you show the condition with inequality f of e less equal than f of e prime?
Yes, I can.
Would you?
Oh, yes. Of course.
Yeah, no, maybe it's just a simple comment, but so if f is injective, right? E equal to e prime is the same as
Wait. F is injected on vertices.
Ah, it's injective on vertex.
Only.
Okay.
No, otherwise it would be.
Otherwise, it would be equality the partial order. Okay.
You look, but it was at least partially my fault that I confused you about the partial order, because I told you that in the context of these pullback theorems, when I'm looking at these graphs E1. So first here I have some conditions on E1. For instance, E1 is a cyclic, right? And so all paths, all finite paths are pointed. But it's very crucial for this pullback theorem to work is that you take the space of all finite paths in E1 and you map it injectively onto all pointed finite paths in E2. Yeah, so in the context of pullback theorems, yes, we do assume injectivity.
Okay, but for the functor, you don't need injectivity.
No.
So,
And in fact, you see, that's this evaluation thing which I like. We should not kill obvious examples. You see, look, this evaluation map. I mean, what's wrong with this example? It works perfectly well. I map my edge E. Sorry. I map E to V, and I map V to V. So I'm by no means injective. And this is a perfectly well-induced star homomorphic evaluation at 1 on the surface.
So, and yeah, maybe another comment. So another, I don't know if it is related, but another case where you have both covariant and contravariant functor is when you have groups that you can have a group sister algebra with. And I mean, all these are groupoid sister algebras. So I don't know if something related, maybe for a abelian group, depending on if you interpret the sister algebra as continuous functions or reduced sister algebra of the dual, you can construct both in both direction functors. It could be something similar, I don't know.
Piotr has an answer.
Not quite an answer, but throughout your talk, I was sort of changing my mind all the time, whether what you're doing is something that is precisely getting a covariant functor from groupoids to C-star algebras. There is a different notion of a morphism of groupoids, which gives a covariant functor into groupoid C-star algebras. And in fact, it deals in a way much more satisfactorily with non-unital situations because it gives you the correct morphisms for non-unital C-star algebras, which is the non-degenerate maps into the multiplier algebras. So is it related? Is it because I've changed my mind already a number of times during your talk about this. So the notion of a morphism of groupoids is not a function, but a relation. And that commutes with all the structure maps. If you have that, then you get a covariant functor into C-star algebras.
That's the venue which we have not explored yet, but it's definitely something.
So we have to do it. I mean, it should not be difficult.
I agree. I mean, it's very recent.
So Piotr was talking about Zakrzewski morphisms. So I'm sure these are not, because we've discussed this.
I forgot.
I forgot.
But
There's a question from Soren.
Oh, sorry. Go ahead. Sorry, I should have seen you here.
Yeah, this is a very vague question, but so I like unital graph algebras, and
So do I.
and then when you like unital graph algebras, you have the problem that the ideals of unital graph algebras are not unital graph algebras.
Yeah.
But what happens is that you can take, if you have a gauge invariant ideal and you unitize it,
Mhm.
it actually becomes a unital graph algebra, and there's sort of procedure which emulates what Dijke, Hong, and Szymanski did. I mean, you know, there's a procedure of, you know, an ideal in a graph algebra, gauge invariant ideal in a graph algebra is a graph algebra itself, but on a secondary, a changed graph where you have to put like infinite number of edges in. I'm mentioning this because when you take the compacts inside the triplets algebra, it's precisely the graph that you get, of course, which because it's the graph of the unitization of the compacts.
Yes.
But I couldn't see it in the other examples. Is this something? Is that just a coincidence, or does it mean anything?
The short answer is I don't know, but that's definitely worth looking at. I'm aware of everything that you just said about these unitizations of ideals, and it's important that you are gauge invariant. However, okay, let me mention one thing, that by the sheer fact of generalizing to morphisms that do not preserve the length of paths, I'm giving up gauge invariance. So
I think that's also true of these unitization graphs, that they are not gauge invariant, I guess. I see. Okay, may not be so useful then, perhaps.
So
okay.
that's you see, we have a gauge equivariant. Sorry, not gauge equivariant. We have a gauge equivariant picture. This is why I got confused with spheres, and luckily Francesca corrected me, because above. Okay, maybe I can draw it quickly before coffee gets cold. So here we have this SUQ2. Oops. But I think it's the button. If you press the button once, you draw this moves. No? Where's the lock? Here. Yes. Okay. Good. Okay. And now what you have here is the Teplitz but tensor product. You mentioned, Francesca mentioned in your talk, right? Tensor product with a circle. So kind of cut off the circle and put it next to the tensor product. And here, what do we have? Here we have a circle. And here we have no, wait a second. Yeah, here you have a circle. So here, what do we have here? A torus, I suppose, yes. Yeah, this will be just a torus. And now this is again a pullback of graph sister algebras, but then it's equivariant. And this is what came out of our trimming theorem with Francesca and Mariusz. But now, if you take fixed points, because the equivariant pullback diagram can take fixed points, and take fixed points, you'll obtain exactly this diagram over here. But the diagram over here is no longer equivalent. I mean, if you look at these are graph sister algebras, all of them. So you obviously have a gauge action, but these star homomorphisms by no means respect gauge action. They actually definitely don't. So yeah, maybe you know, there are many venues of exploration, groupoids, there's unitization of ideals, and so on and so forth. Yeah, that's. But we first wanted to somehow get examples and results to be motivated. I'm not interested in abstract nonsense. I just want to have tools that explain and compute as much as possible. So this is why we first focused on you know, theorems like such and such a thing is a pullback. what I showed you in the slide is just the tip of an iceberg. Already in the published version, we had a far more general theorem about the pullback, where you can augment graphs over things by some whatever other things. And these theorems are far more general. So that's first, I want to have really new pullback theorems that, for instance, allow you to understand some CW complex structure or compute K groups or find generators of K groups. And then I want to explore how I can understand what I just did. Okay. So I definitely am very happy with all these suggestions and questions, but somehow for us it was of secondary importance. We definitely want to do it, but we haven't done it yet. Alex. No.
Just do it. Just talk.
Hi, can you hear me now?
Yes.
Okay, perfect.
Very well.
Yeah, so like I was thinking, so the first thing is like as for graph algebras, and like tuplets algebras, you can consider like pullbacks of tuplets algebras for graphs and tuplets algebras of
And now I say tablet algebras, you mean like the completions of conpath algebra?
yes,
Okay,
correct,
okay.
exactly. And so like what you would notice is like, for at least if you have like something like surjective morphisms or something like this, then you would always get something like a pullback diagram for their cone path algebras in this context, I guess. And like not all, but not always like one for the Levitt path algebras. And so I was thinking like you could do maybe something like this also for these kind of like more general diagrams where you don't have like surjective morphisms or something like this, but where you have like something like an embedding of a point into a circle, right? Like the one on the left bottom.
But are you talking about contravariant induction or
I'm talking about covariant.
covariant?
Yes, covariant.
Okay.
And it would be something like if you have, for example, if you have a group G and a group H, and you have a homomorphism of a group G into a group H, and then you would consider, for instance, like
Group rings. Yeah.
yes, group rings or group C star algebras, right? I'm like,
Yes,
so
yes, yes.
that would induce that would
Covariant.
generally induce like a
Covariant.
morphism,
Yeah.
covariant morphism.
Sure.
But the issue with cone path algebras
Mhm.
that I would think is like what's happening here is like that you have, for example, if you, because you don't have a group with a single object, but with multiple objects, you can
Yes.
have that like some morphisms don't match up with range
Yes.
and source,
Yes.
and so they would have like they would produce 0 as a composition inside your group algebra. But if you, for example, have a morphism that goes from one group tree, one half category here in your case into the other one, then it suddenly might be able to match up again accidentally. That's what you have like surjectivity on vertices, right? Injectivity on vertices. And so I think this should be like this should be also like the phenomenon driving these kind of pullbacks diagrams in more general, like so that like if you have any kind of like covariant functor from one path category into the other one, this should be the only source which prevents pullback diagrams of cone path algebras. And then like from there, you should be able like to find something like a pullback result for those. And because like, so you have some phenomenon of like that for graph algebras, if you pass from triplets to graph algebras, and you could think of like, this is something not quite covariant. And so you should be able to see something like a pullback diagram of relative Levitt path algebras, which you should be able like to might be able to figure out like also like that when is such a pullback diagram, when does it induce exactly a pullback diagram of their absolute Levitt path algebras.
It's a suggestion of the
As
question.
a suggestion, yes.
Well, let me answer it in the following way. It is true that every conpav algebra is a Levit-Pav algebra, but not the other way around. So yes, of course, that's one of the things which I didn't mention, but you have so-called relative conpav algebras. And I know that you have some nice approximating arguments for pullbacks using this theory of relativity. You see, when you define the conpav algebra, well, you don't have to be, so this is also known as the absolute conpav algebra, because I ignored all regular vertices, okay? But what I can do, as Alex suggests, I can pick up some arbitrary subset X inside the set of regular vertices of E. And I can say, aha, I impose my second type conjugate relation only at vertices belonging to X. So this is like partial, it's in between. So the moment X is all regular vertices, I have Levit. And when X is the empty set, I have the absolute conpav algebra. So, so it is, I definitely agree. It's interesting to see what would be, I mean, I gave you the requirements for induction between conpav algebra. They are far more relaxed, but I cannot handle every Levit-Pav algebra as a conpav algebra, because it's not the case. I mean, not every Levit-Pav algebra is a conpav. So these conjugate relations cannot be cheated away. But of course, you can have some other pullback theorems for the step in between for the Teplis algebras, and maybe the step in between is a good way to prove some end results which are in the realm of graph sister algebras. So yeah, that's my answer to your question. And also, I'm not sure I completely answered the question about these groups. So yes, of course, when you have a group, you have two obvious constructions of Hopf algebras. You can take a finite group to focus attention. You can have a group ring, or you can have functions on the group. But the moment you go beyond the infinite sets and you want to somehow make sense of what you're doing, I mean, these objects are no longer the same, right, Piotr? I mean, this is, it's different to have a convolution sister algebra and different to have a function on a group sister algebra. These are different animals. So one of the things which is in contradistinction to the group case, when we do our functors, our objects are always constructed in the same way. I have my graph, and I have my graph sister algebra, Levit-Pav algebra, whatever you want. We play with morphisms only. We somehow do not discriminate against graphs. We like all graphs. Of course, we single out graphs with finitely many vertices because of unitality. Okay? But maybe let me end by emphasizing one more time this comment about mapping into pointed paths. Because over there you have a bijection. So if I could make sense, if I could make sense out of these conditions by saying, all right, in fact, this morphism is not from F1 to F2, but it's from F2 to F1. But now I have to say I take a graph and I take all pointed finite paths in my graph and I map it bijectively to all finite paths in the other graph. If I can somehow make sense out of it as a morphism, give a category like this, then this would be a contravariant induction. And there is a chance that it would be a genuine push out to pullback theorem. But I was kind of scared of how general it would be. I mean, this procedure is a little bit awkward. I know that there are unbounded operators which are only densely defined and the domain is not everything, but it's kind of this reduction from all finite paths just to pointed paths and then demanding everything to be bijective. I don't know. I mean, somehow for me, it was too particular, but maybe it's definitely one of the starting points.
And so I still had another comment, like based on the group point perspective. So what I felt like was like always that like this path categories perspective is about like finite paths, like matching up finite paths in your graph algebras, kind of like. And for the groupoid, like morphisms or relations between them, it's more about like also like thinking about infinite paths.
Yes,
and
definitely. Yeah, you're right. Yes.
Yes, and I think so. That's something like a driver behind like there's this famous isomorphism between O2 and O2 minus, like where you know the isomorphism based on the K theory and classification, and but like the matching up of like paths is not clear. So there's like there's no concrete morphism known, concrete isomorphism known, and I think that's something maybe that like what Piotr mentioned, that sort of like the other Piotr,
Yeah.
like some morphisms between groupoids or relations between groupoids. Maybe that could be something.
Since this is not a question, I don't need to answer.
Yeah, that's just like a suggestion.
Thank you.
Also, I have a question. Is this morphism going to preserve the diagonals? When you build the homomorphism in the graph-system algebras?
And how I view see the diagonal in terms of finite path?
It's the subalgebra generated by the S alpha stars.
Okay, as alpha star. And alpha star are paths,
Alpha is the path, yes.
then it should preserve
It
it.
should preserve. So I
yeah,
guess you're
definitely.
gonna get some kind of a continuous function, I guess, done the other way around between the boundary path spaces. So I guess that's something else to do.
Yeah.
You can try to look at because if the graph has no sinks, of course, and it's not the most interesting example here, but the graph has no sinks, it's finite, then you're gonna have some kind of symbolic dynamics. And it looks like this morphism is some kind of this block code they have there in symbolic dynamics, that you can always describe these continuous shift invariant maps between the symbolic dynamics using the code maps. And it seems like the map F that you have is some kind of the inverse of the code map. So I guess it's maybe something also that's interesting to look at.
I would be very happy to you explaining it to me in Warsaw.
Okay.
Soren is happy with the comment, I think.
Are there any other questions, comments, or anything from online participants?
Soren is happy.
Okay, well, let's thank Piotr again.
Obrigado.
Now it's coffee break.
And I stopped the recording.